We will wait another 2-3 minutes just to give people who are a bit late the chance to be here. A very warm welcome to you all for this Allison-Levick Lecture in 2023. A special welcome to all children in the audience and anyone who is for the first time in their life on their university campus. I hope you're as nervous as I was when I was first on a campus. Fortunately, that has ceded a little bit since my first time. Let me first give an acknowledgement of country. We acknowledge the traditional custodians of the land upon which this university is situated, the Wallamadical people of the Darug Nation, whose cultures and customs have nurtured and continue to nurture this land since the Dreamtime. We pay our respects to the Darug people and the Wallamadical clan, their elders past and present. We further wish to honor and pay our respects to the ancestors and spirits of this land, and humbly ask that all members of the Macquarie University community are granted with the capacity to wingara, to think, to learn, and to walk safely upon this pemul, this land. The university continues to develop respectful and reciprocal relationships with all Indigenous people in Australia and with other Indigenous people throughout the world. My name is Samuel Muller. I have the privilege to be the head of the School of Mathematical and Physical Sciences, which got founded 2 years ago, and it is exciting to have you all here. In order to make sure that we are all safe and know where to go, just in any case, the exits are up at the back and where you came in. In the unlikely case of an emergency, I suggest we take all this door and then keep going. There are a couple of flagpoles outside, a grassy area. This would be the assembly area. It is my privilege to now introduce our host for the evening, Professor Fred Watson. Fred is Australia's first astronomer at large in the Commonwealth Department of Industry, Science, Energy and Resources, having worked at both of Britain's Royal Observatories before joining the Australian Astronomical Observatory as astronomer in charge in 1995. Fred is recognized internationally for helping to pioneer the use of fiber optics in astronomy during the 1980s. He's best known today for his award-winning radio and TV broadcasts, books, music, and dark sky advocacy. In 2003, Fred received the David Allen Prize for communicating astronomy to the public, and in 2006 he was the winner of the Australian Government Eureka Prize for promoting understanding of science. In January 2010, Fred was made a member of the Order of Australia for service to astronomy, particularly the promotion and popularisation of space science through public outreach. Over to you, Fred.
Thank you very much, Sam. Thank you. And thank you, everybody. That means I don't need this bit of paper now, because that's what it says, all that stuff. No, it doesn't. But unfortunately, I'm past the age where you can memorize lots of introductions and things of that sort, so I'm going to read this. But I do acknowledge, thank you, you're welcome, Sam. It is a great pleasure to be here. It's fantastic to see you all here as well for this 2023 Allison-Levick Lecture. So, as it says here, it's my great pleasure to welcome you to this 2023 Allison-Levick Lecture, and I'd like to add my own acknowledgement of the traditional owners of the country, the Wattamatagal clan of the Darug Nation, and pay my respects to elders past, present and upcoming. They were the first astronomers. The annual Allison-Levick Lecture is funded by a bequest from a Mr. Jack Allison-Levick, a Melbourne psychiatrist who had a lifelong interest in astronomy. Mr. Allison-Levick had seen the spectacular astronomical photographs made using the telescopes of the former Australian Astronomical Observatory by pioneering astrophotographer Professor David Malin, who I'm delighted to say is in the audience tonight. Stand up, David, so everybody can give you a clap. This man... Without this gentleman's absolutely fundamental ability to put colour into the stars, the man who coloured the stars, this wouldn't be happening tonight. So it's a great pleasure to have David with us this evening. Jack Allison-Levick was inspired to leave money in his will for talks that would enhance the public understanding of astronomy. And the first Allison-Levick Lecture was presented by David himself at the Powerhouse Museum on the 11th of July 2003. The Allison-Levick Fund is now administered by the Department of Industry, Science and Resources, and the lecture hosted by Macquarie University is the current home of the Sydney division of the former Australian Astronomical Observatory. In the 20 years since the lecture's inauguration, we've had a succession of distinguished astronomers and space scientists who have led us through the whole sweep of space-time in their presentations. The topics have ranged from the planet Saturn, that's the wrong piece of paper, delivered by NASA's Cassini mission project scientist, Dr. Linda Spilker. Who was here for that talk? That was sensational. Yes, quite a number of you. That ranges from that to spinning neutron stars, delivered by the original discoverer of such objects, Dame Jocelyn Bell Burnell, and beyond. And by a happy coincidence, this year's lecture falls hot on the heels of one of the year's most significant discoveries in the field of fast radio bursts, which my broadcasting colleagues tell me should be articulated fast radio bursts. That's how it should be said. This Australian discovery concerns the furthest known of these mysterious objects that has been found at an eye-watering distance from our galaxy. I didn't want to spoil the fun by telling you how far away it is, but it's a very long walk. We're very fortunate to have the lead author of the discovery paper to present the 20th Allison-Levick Lecture. Dr. Stuart Ryder is an adjunct fellow in the School of Mathematical and Physical Sciences here at Macquarie University and a member of the university's Astrophysics and Space Technologies Research Centre. He also works as a programme manager for Astronomy Australia Limited, overseeing Australia's usage of the European Southern Observatory and the Vera C. Rubin Observatory facilities in Chile. As a member of the Commensal Real-Time ASCAP Fast Transient Survey Team, and that abbreviates to CRAFT, which is a lot easier to say than Commensal Real-Time ASCAP Fast Transient Survey Team. As a member of that, Stuart and his colleagues have been using the European Southern Observatory's very large telescope to hunt down the host galaxies of fast radio bursts discovered with the ASCAP Radio Telescope Array on Wadri Country in Western Australia. Stuart is also an avid eclipse chaser, having travelled to experience 11 total solar eclipses since 1991, some of which I've had the pleasure of accompanying him to. Ladies and gentlemen, then, would you please welcome Stuart Ryder to give the 2023 Allison-Levick Lecture on fantastic radio beasts and where to find them. Thank you very much.
Thank you very much, Fred, for that very warm welcome. And I'd like to welcome everyone here tonight. But I don't want to give you a lecture, because I know what sitting in a lecture theatre like this can be. I want to tell you a story. And so like any good story, it has to have a title. So with apologies to J.K. Rowling and many fans, I've borrowed from the title Fantastic Beasts and Where to Find Them. Instead, I'm going to tell you specifically about fantastic radio beasts, or conveniently FRBs, and where they can be found. But I'd also like to start by acknowledging the traditional owners of the land on which Macquarie University is situated, the Wallumattagal clan of the Darug Nation, and pay my respects to their elders, past, present and emerging. So I'm just going to tell you a bit about what we know about FRBs. This is going to be a very short history because we've only known about these objects for less than 2 decades. I'm going to tell you about how we went about finding FRBs, and in particular, what it took to trace them back to their point of origin. I'll then hopefully share with you some of the excitement that came with our very recent discovery that Fred mentioned about finding the most distant FRB ever known. And then I'll tell you a bit about all the wonderful things we can actually do with fast radio bursts once we have enough of them. In particular, what we're looking forward to being able to do with FRBs in the future. So, what is an FRB? Well, FRB officially stands for Fast Radio Burst, but I reckon we missed a good opportunity. We should have called them Fantastic Radio Beasts from the beginning, but unfortunately, instead we did what Australians tend to do. We called them what they are. They are Fast Radio Bursts because they are fast, in the sense that the length of the emission that we see is typically less than a few thousandths of a second, a few milliseconds. Radio, because pretty much all the emission that we've ever seen from a FRB is confined to the radio part of the spectrum. And in fact, it doesn't even fill the entire radio band. We've never seen a counterpart to a fast radio burst at any other wavelength for an FRB outside of our galaxy. So that tells us that something really strange is going on, because most objects that we do find, we can detect them at more than one wavelength, not FRBs. And bursts, because, well, as the name implies, we see a burst of radiation and then nothing. We never see them again. Well, all right. There are a few which appear to repeat, and I'll come back to those later, but they're definitely in the minority. And so whatever it is, you think, well, if we only ever see one burst, it's probably something that blew up and isn't there anymore. That may be the case. We'll find out shortly. But what we have worked out is that based on the rates that we've been finding these things as we began to realise that they exist and how to look for them, it's now clear that these FRBs occur at rates of a few thousand, maybe tens of thousands, across the whole sky every day. And yet we didn't even know these things existed until 2007. It's like, well, how could you miss something that's so obvious? I mean, and so common? Well, it comes down to a number of factors. Obviously, they're very short, and they're going off at random across the whole sky, so it's very difficult to know where to be pointing at any given time. So in fact, the field of fast radio bursts grew out of pulsar astronomy, because they're, as you'll see, they're kind of related phenomena, but clearly very different. So as Fred sort of alluded to, the first pulsar was discovered by the then PhD student, Jocelyn Bell, now Dame Jocelyn Bell Burnell, when she was still a PhD student at Cambridge in 1967. And those of you who came to her Allison-Levick Lecture here just a few years ago would have been captivated by the wonderful story that she was able to tell about discovering the first pulsar, or as she called him, or some people called him, LGM1, which apparently stood for Little Green Men, but I think that was just a bit of a joke to see if people could cotton on to what might be going on here. But once she started finding more and more of these things, all with similar but different properties, it became pretty clear that they probably weren't signs of ET. And in fact, we already had a pretty good theory for what they might be, unlike fast radio bursts. So people had hypothesized that when a massive star, something 10 times more massive than our own sun, for instance, when it reaches the end of its life, having used up much of the fuel in its core, and sometimes the most massive stars can do this just within a few tens of millions of years, so not very long at all. But when they run out of fuel, the core will collapse because there's not enough energy being generated to resist gravity. The outer layers will be thrown off in a supernova explosion. The core part, however, if it's massive enough, will collapse to form a black hole. But if it's not quite massive enough, instead it will become what's called a neutron star. And as the name implies, that's a star made entirely of neutrons. So all the other atoms, the protons, the electrons going around, they all get squashed together, forms just neutrons. And that means you can finish up with an object that is, have a mass comparable to our own sun, but because of gravitational pressure, it occupies a size no bigger than a city, a few kilometres in size. So that's an incredibly dense state of matter. Typically, these massive stars would have had a magnetic field associated with them before they exploded and collapsed. They still retain that magnetic field even when they shrink down. But in so doing, that magnetic field becomes very intense, much stronger than what you get from an MRI machine or something like that. And as a result, any radiation from these neutron stars can really only escape along the polar regions. But then depending on the angle at which these neutron stars are spinning, and they do this very, very quickly because, of course, they used to be a very big star, rotating slowly, but once you shrink them down, angular momentum conservation says, well, they must spin very, very fast. And so it became clear that probably what pulsars are, in our good confirmation of this, that objects, very dense neutron stars, that we just happen to be along the right sight line, so much like a lighthouse beam going around, we will see these regular pulses or flashes of light, but they are extremely regular. They are the most accurate clocks that we have in the universe, more accurate than even our own atomic clocks. So they're really, really useful, but they're also very repetitive, very regular, unlike FRBs. And this is a picture I took of Jocelyn. Fred and I were recently on a tour in the UK, and we had the joy and privilege to be joined by Jocelyn for part of that tour. And so I hope you'll be pleased to know that she's still doing extremely well, even at 80 years of age. So the thing about pulsars, apart from the fact that they have very regular pulses, is that so far we've only ever found them in our own Milky Way galaxy and in a few outlying regions of our galaxy. And the thing about their pulses is that they undergo this interesting phenomenon called dispersion. And what this means is that whenever a pulse of, well, in fact all radiation, but particularly if we see it as a pulse, passes through a medium, a gas, let's say, which is extremely hot, and that could be because it's been heated by nearby stars, or it could be the passage of a shock wave or something that gets that gas really excited and very hot. It can free the electrons from their atoms, and these electrons are then free to wander through space. But whenever a pulse of radiation passes through them, they introduce this interesting effect called dispersion, and that means that the lower frequencies get slowed down relative to the higher frequencies. And as a result, what was originally a pulse at the same time at all frequencies, by the time it arrives on Earth, we see a delay. And the more of this dispersion, the larger the delay at lower frequencies. So for instance, if we compare the signals coming from a pulsar and a nearby spiral arm of a galaxy, let's say, we will measure a certain amount of that dispersion. But if we were to look at an object which is much further away and would have travelled through more of this material, we see even more dispersion. So this dispersion, if you like, is a proxy for distance. It gives some idea roughly how far away these pulsars actually are within our own Milky Way galaxy. But we know that our Milky Way is finite. It's not bigger than a few tens of thousands of light years. And so there's a certain limit to how much dispersion we might expect to see in a pulsar's pulses. But back in mid-2000s, an astronomer called Duncan Lorimer and his colleagues decided that they wanted to go back and look at some old data taken with the Parkes telescope, now known as Murriyang. It was taken back in 2001 as part of a search for new pulsars. But they realised that the original search probably hadn't been expansive enough, that they'd only searched a fairly small range of dispersion, so to speak. And so they simply reanalysed the data, but over a much larger range of dispersion, hoping to find maybe some more distant pulsars or something. But the only thing they found was this very strange one-off burst, so not pulses, but only a single trace of a pulse that had a very large dispersion. In fact, it was so much larger than any other pulsar in that direction that they hypothesised, well, in fact, it probably doesn't come from our own galaxy. It must have come from outside of that. And they realised, well, gee, if there are these objects emitting such bright pulses, even if they're only one-off events, if we could work out where they came from and how far away they've travelled, we could use these pulses and their dispersion to tell us really interesting things about the stuff between galaxies. So that was a pretty bold prediction, given they only had one burst. It was called the Lorimer burst. It wasn't called a fast radio burst because we didn't think there was a class of things. We only knew of one, and everyone called it Lorimer burst after the guy who first published it in the journal Science, in fact 2007. So 6 years after the event actually happened, it was finally out there in the literature. So I think that's a great recognition of the effort and the confidence that Duncan and his colleagues had to publish such a strange, bizarre finding that just earlier this year, Duncan and his colleagues Maura McLaughlin and Matthew Bales, who's at Swinburne University in Melbourne, were awarded the 2023 Shaw Prize in Astronomy. I mean, this is like the Nobels of science, albeit they are not the Nobel Prize, not as well known, but it's certainly a prestigious prize that recognised the fact that they had not just stumbled across an interesting new phenomena, but they had the courage to put it out there and say, look, we don't really understand what these objects are yet, but we believe there'll be many more of them, and if we can use them as tools, we could learn so much about the universe. But if you ask Duncan himself what the most exciting recognition is probably not the Shaw Prize. It's the fact that there's a rock band, a music band called Lorimer Burst. Not a song, an actual band that decided that they loved the name Lorimer Burst, that they would call themselves Lorimer Burst. So you know you've reached the zeitgeist when you actually have a band, a music band named after a phenomenon that you discovered. However, like every new phenomena, the path to discovery was somewhat rocky. And so I have to tell you about a phenomenon we call peritons. So shortly after the first Lorimer Burst was published, people started looking at new signals coming off the Parkes telescope, and they noticed a few things that looked, well, kind of like a fast radio burst. You know, you can definitely see that sort of sweep type behaviour, a delay in the arrival times at lower frequencies, and yet not like fast radio bursts. So for instance, for various reasons, it was pretty clear they were actually coming from much closer. In fact, probably somewhere on planet Earth and not at large distances, despite that apparent dispersion. Interestingly, they seem to occur more often during the daytime, specifically on work days, less so on weekends. And yet they didn't show, if they were, we know we get all kinds of interference signals with radio telescopes all the time, especially nowadays thanks to mobile phones, digital television. But the thing about those is that they're so close, there's almost no dispersion introduced. And so you see that as a vertical line. You see the same pulse arriving at all frequencies at the same time. So it couldn't be the normal sources of terrestrial interference. So what were peritons? Well, it took some detailed investigative work by a PhD student, Emily Petroff and her colleagues, to do a bit more analysis, and they finally realised, in fact, these things weren't just more common on weekdays, they were more common around lunchtime and at dinner time. So that got them thinking, what might that be? And then they thought, well, maybe it's the fact we have microwave ovens at Parkes Observatory, always telling people please don't use them, but sometimes people just want to heat their lunch up in a hurry. So they ran a few microwave ovens, but pointed the telescope in the direction of the observing quarter, but they couldn't see any. There was no signals, there was nothing there. Until one of the staff got up, instead of waiting for the microwave to finish its cycle, they opened the door, like we all do because we're in a hurry, before it had properly shut off. And enough radiation was able to escape through the door at that point to produce these periton-like signals. So of all things that we never really thought microwave ovens, but hey, it just underlies the difficulty that we face in dealing with sources of interference, how they can easily mislead you. In fact, for a long time, many people thought, well, probably the Lorimer burst was just another type of periton, and maybe they're not real. And indeed, the first few FRBs that were found in the first 5 years or so, they were only being found at Parkes. So obviously that's a bit of a worry. So it was somewhat of a relief that eventually people at other telescopes did start seeing FRB-like signals. So for instance, the Arecibo dish, which is this large fixed reflector in the ground in Arecibo in Puerto Rico, which unfortunately, as many of you know, underwent a catastrophic collapse, or at least the support towers for the focus cabin collapsed 5 years ago, and unfortunately the whole facility is now decommissioned. Fortunately, around the same time though, China has deployed what they call the FAST, the 500-metre aperture spherical telescope, similar design, but even bigger than Arecibo. And it's now started finding fast radio bursts as well. And also large, fully steerable dishes up to about 100 metres in diameter, like the Greenbank telescope, have also started finding FRB. So, phew, they are a real thing. They're not just a Parkes phenomenon. The thing about these large single dishes, though, is that they have great sensitivity, large collecting area, that's what you want. But they define what we call their beam, which effectively is like their field of view, okay? And for any one of these large dishes, that field of view, that patch of sky they can see at any given time, is somewhere between 0.5% and maybe 10% of the size of the full moon, which is a pretty small patch of sky, really. And so your odds of picking up one of these fast radio bursts going off at random are pretty small. But at least if it does go off within your beam, you've got a good chance of getting a good high signal to noise result. But the problem then is that you don't know where within that beam size the event actually happened. So, if it is something the size of the full moon or a bit less, when you go looking at a patch of sky, or an optical map, or photographs that David has taken over the years, and more recently electronic images, and you'll see hundreds, maybe even thousands of galaxies within that patch of sky. And it's impossible to work out which of those actually was the source of the FRB. Things changed a lot though with this particular telescope, called CHIME, which stands for Canadian H1 Mapping Experiment, which, as the name implies, doesn't have FRB in it, and yet it turned out to be just the thing for finding FRBs. So it doesn't look like a normal telescope. It actually looks like a series of skateboard half pipes, if you like, made out of wire mesh. Not particularly sophisticated, but there's a lot of collecting area there. That's good. And although you can't point it or steer it, you don't need to. The sky passes through the field of view of CHIME every day and does this over and over again. And so today, the most prolific FRB finding machine is CHIME. However, like the large single dishes, it can't really tell you where exactly in the sky that burst came from. But one thing that it's done remarkably well, though, is it's enabled us to see a number of these sources that come through the beam around the same time each day with almost identical amount of dispersion. So it clearly come from the same patch of sky. They're probably the same object, but just emitting more than one burst. However, these repeat bursts, they don't do it on anything like a pulsar regularity. And in fact, it's more like what I might call windows of repeatability. So there are certain periods of time during which seeing a repeat burst is more likely, but it's not guaranteed. But nevertheless, the fact that there are a small percentage of these FRBs do appear to repeat. The first of those was found with Arecibo back in 2012. And then a few years later, it was realised that, again, for the same patch of sky coming overhead, they saw a series of bursts, about 10 in the space of 2 months. But again, all with almost exactly that same amount of dispersion. That suggests it was probably come from the same object. So this opens up a couple of interesting consequences. One is that, well, if an FRB can repeat, clearly it can't be a catastrophic event, otherwise there'd be no chance of it repeating. So at least some FRBs must come from objects that don't destroy themselves. Okay, we're not sure what they are yet, but that's one clue. But the other interesting thing is that what it suggests is that if you are patient enough and you could get enough observing time on what we call an interferometer, that is an array of dishes, something like the Australia Telescope Compact Array, just outside of Narrabri here, or its bigger cousin in the Northern Hemisphere, the Very Large Array in the USA. If you were to point an array like that at that patch of sky during one of these windows of repeatability and keep your fingers crossed, eventually, hopefully, you'll see a burst go off and you'll be able to make an image of that patch of sky with a much, much better spatial resolution than the single dish can do. In fact, it should get you down to sort of what we call an arc second in scale. That's about 1/2000th the width of a full moon. But if you've got a position to that accuracy, then when you go and look at an optical image of the sky, it's going to be pretty clear which galaxy it came from. So for the first time, back in 2017, we were able to localize, in other words, find the origin host galaxy for this object, 2012-1102. And it turned out to match a dwarf galaxy, so something much smaller than our Milky Way, less than 10% of its size, but actually a quite actively star-forming galaxy. So I know there's a lot more star formation, well, in fact, as much star formation happening in that dwarf galaxy as in our entire Milky Way. And so this led to an interesting possibility. People thought, well, okay, if there are active star formation happening, new stars being born all the time, there's an increased likelihood that some of those will become a supernova explosion, and that what's left behind might be not just a neutron star, but an extremely magnetic version of a neutron star, which are themselves already highly magnetic. But let's suppose that you could supersize that and have extremely strong magnetic fields. And we have already seen objects kind of like this in our own Milky Way galaxy. We call them magnetars. But the thing about magnetars, because of the very strong magnetic field, just like our own sun has a magnetic field, and occasionally those magnetic field lines they get twisted and all loop together, and eventually they have to snap. And when they do that, and then they reconnect eventually, but as they snap, they can release enormous amounts of high-energy radiation. We see this here on Earth a few days later as beautiful auroral displays. Hopefully some of you might have had the chance to witness. There have been some fantastic auroral displays in the last few months as the sun level of solar activity increases, and more of these solar flares happen as these field lines on the sun snap and reconnect. And we think a similar phenomenon might be happening around these magnetars, and potentially it's thought that might release enough energy in a short enough period of time to give you an FRB-like signal. but it's just a theory still. But at least having found the host galaxy for a repeating FRB suggests that maybe magnetars are the source of FRB emission, right? Well, maybe. The next one, well, one of the next ones that we were able to localise in 2020, 0120, so 20th of January 2020, that's how we name these things, turned out to come from a relatively nearby galaxy to our own called M81. It's a very similar scale to our Milky Way. But in fact, let me just change the lighting here a bit, folks, so you can hopefully see that better. It's what didn't come from the inner part of the galaxy, it came from way, way in the outskirts, way out here. And in fact, we were able to match it up with the known location of what we call a globular cluster. Now, this is not the globular cluster in that location. This is one in our own Milky Way galaxy that I've shown just to give you an idea of what they're beautiful clusters of stars. But the thing about a globular cluster, I like to think of these as stellar retirement homes. They are full of old stars. There hasn't been any star formation in globular clusters for at least half the age of the universe. So how can you have a magnetar, which is the product of recent star formation and recent supernova, happen in a globular cluster? It just doesn't make sense. So something else is going on here, and we haven't really figured that out. But the thing about, I've shown you two so far, two FRBs have been traced at host galaxy, but they're both the repeaters, the ones that we can go and stare at later on with an interferometer and make an image. But these are just a small minority of all the FRBs that are now being found. So what about the ones that don't repeat? Where do they come from? Well, that's a much harder problem because you're dealing with a situation where you're trying to detect an object in real time. You don't know where and when the next one is going to be. So how do you optimize your chance of finding it? So you really want two things. You'd like to have the ability to see over a very wide field of view, not just that narrow beam of a single large dish, which is less than the size of a full moon. Ideally, you'd want something that has the area of coverage of sky, let's say tens, maybe hundreds of times the size of a full moon. So at least you're just increasing your odds of seeing something going off in that patch of sky. But at the same time, you'd also like the power of an array of dishes like the VLA, like the compact array, spread over many kilometres, because that gives you that imaging power that enables you to make an image at very high spatial resolution and work out exactly where within that very large field of view that burst came from. And there just aren't telescopes like this. Well, except for one. Let me introduce you to ASCAP. ASCAP stands for Australian Square Kilometre Array Pathfinder. So as the name implies, it's a pathfinder or a precursor to the Square Kilometre Array, which is the next generation of radio telescope. It's currently just begun construction in two places. One is the remote outback regions of Western Australia, I'll show you in a minute. Another part of it is being built in South Africa. So it's a major joint international project in which Australia is a big partner. But in the lead up to that, Australia, like other countries, decide they need to test, prototype a lot of technology that would go into SKA. And the fantastic thing that Australia decided to do is that they would focus on two things, a wide field of view telescope and an interferometer in one. And yet, this whole ASCAP thing was planned before fast radio bursts were even known about. But if we were going to design and build a fast radio burst detector, we would have wanted something like ASCAP. Thankfully, it was already being planned and built to do surveys. So what it consists of 36 dishes, each of them is 12 metres in size, so not large by Parkes standards. But what's important is that each of these dishes has not just a single beam, but effectively 188 beams. So we have an array of detectors on each of the dishes that gives them a field of view, 30 square degrees, that may not mean much, that's over 100 times the size of a full moon, instantaneously, each antenna can see. But within that field of view, ASCAP is constantly making images with resolutions of an arc second or better. So we could potentially use this to help us localise where fast radio bursts come from, if we have the right technology. And we do. But what's important, so several other things. So ASCAP is located on Inyaramana Ilgari Bundara, which is the CSIRO who operate the facility, the Murchison Radio Astronomy Observatory. Inyaramana Ilgari Bundara stands for Sharing Sky and Stars in the local Wadri language, who are the custodians of the land on ASCAP. I think it's a lovely concept. It really underscores the fact that we are sharing this fantastic location. It is one of the most radio quiet areas in Australia, let alone the world, and it's protected by legislation now. So you can't go anywhere near the site with your mobile phone or any kind of stuff, which actually makes building the Square Kilometre Array in such a location a particular challenge. But nevertheless, it is one of the world's best sites to do radio astronomy. So let me just show you what ASCAP looks like, in case you haven't seen it before. So here we are in our standard drone footage flying across the Murchison region, and here is ASCAP, which, as you can see, consists of 36 of these antennas. They're all fixed in position, but you can see some of them sort of clustered close together, some of them much further apart. But they all work in unison, and they're currently conducting 5-year surveys for a whole range of different projects. Now, our particular project, looking at fast radio bursts, we don't need any observing time. We don't know where the next radio burst is going to come from. So we simply piggyback on other surveys as they happen. And so we're getting bonus science, if you like, out of it. We don't have to interrupt or take away observing time for these other surveys. We can just simply come along for the ride and eavesdrop. And as I mentioned, each of these antennas, so we're now looking from the dish out through the top of each dish, has these phased array feeds. So you might just be able to make out the sort of checkerboard pattern. That's what gives us that fantastic wide field of view. And as a result, we can capture, hopefully, increase our odds of seeing a fast radio burst, and when we get one, we'll be able to have an image that can then show us where exactly that burst occurred. Sounds simple. It actually turned out to be a very complex problem. It took us many years to solve it, but thankfully, when we did, in the group that did this work, of which I am a part, is called, as Fred mentioned, CRAFT, the commensal meaning we do it at the same time as other surveys. Real time, because we're trying to find these bursts as they happen, ASCAP Fast Transient Survey. So it was started and led by three key people: Ryan Shannon at Swinburne University, Keith Panister at CSIRO here in Sydney. He's if you really like the brains trust, he's the engineer who developed the fantastic technology that makes this FRB detection possible. And Jean-Pierre Macquarie at Curtin University, who was a fantastic theorist who dreamed up all the things we could do with FRBs. We have about 50 collaborators in the team, mainly in Australia, but also in the US and in Chile. So on 24th of September 2018, after much frustration, we finally got our first FRB detection and localization with ASCAP. And indeed, we didn't just work out its position to 1 arc second, we were able to get it to a position of 0.1 of an arc second, which just blew everybody away. We really thought, wow, this is incredible. So we then sent the coordinates for this particular object to our colleagues in Chile. So as I'll come to later on, Australia is in a very privileged position right now where we have direct access, or the ability to apply for time and get observing time on these wonderful facilities, the world's best, most powerful suite of optical and infrared telescopes on the planet. The European Southern Observatory is a very large telescope. In fact, there are 4 very large telescopes. You see 3 of them here. Each of them has an 8-metre mirror, and each of them is equipped with a whole bunch of different instruments. They can all work together as one for certain types of science, or they can work independently. In this case, we were just using one of the telescopes with a very sophisticated digital camera. It's arguably these days not necessarily anymore in no larger in collecting area or in numbers of pixels than on your mobile phone these days. But when you put them on the back of an 8-metre telescope, you can do some incredible things with it. So they sent us back an image of that field, and we then put this little tiny black circle, that's how precise we were able to pin down the location of this first FRB. So it turns out it's coming from a galaxy, and based on the brightness and its distance that we were able to infer, we were able to work out it's actually not a dwarf galaxy like that first repeater. It's something much more akin to our own Milky Way in terms of its size and its star-forming activity. But in this case, it's 3.5 billion light years away. So this was quite a breakthrough result because no one else had the ability to do this kind of pinpointing of FRBs if they didn't repeat. We were the first to do that. And so we submitted this paper to a prestigious journal, Science, which takes a lot of effort. It gets multiple reviews. The journals are very selective about which papers that they even publish, let alone they send out for refereeing. But after a lot of to and fro, we eventually got the paper accepted. And actually what surprised us was not so much that it got accepted, but a year or so later we were informed that this particular paper had been awarded the American Association for the Advancement of Science's Newcomb-Cleveland Prize. Not the Short Prize, but still a nice thing to be awarded. And that is handed out every year for the most impactful paper published in the journal Science the previous year. Not just in astronomy, across all fields of science. So the editors had recognised, well, gee, there really is something in this, and so that was worth highlighting, but certainly wasn't the kind of honour that we expected, but we were very pleased to get that kind of acknowledgement. Since that time, the last 5 years, we've gone on to localise a couple of dozen more of these non-repeating fast radio bursts, and then we using the telescopes in Chile, we've managed to get the beautiful rogues gallery, if you like, of images of host galaxies. These are produced by my PhD student here at Macquarie University, Lachlan Marnock. You can see Lachlan here at sunset. We had the privilege back in 2019 to actually travel to Chile to carry out some of the observations by ourselves. Of course, COVID intervened, and so we haven't been able to make those trips to Chile as often, but instead we simply send the coordinates that we've just obtained for our FRBs, and the wonderful staff at ESO in Chile conduct the observations for us. They send us the raw data, and Lachlan does his magic on them and produces these beautiful images and compares them to the locations of the FRBs that we find. And you can see that most of them, they certainly generally don't lie on the centres of galaxies. They tend to, again, in the outskirts. A few of them definitely associated with the spiral arm features, probably sites of recent massive star formation, so kind of consistent with that magnetar model, but not all of them. Trouble is, as they get further and further away, it gets a lot harder to work out if there really are spiral arms there or what sort of star formation, so exactly what causes them. So some of them might actually overlap with globular clusters, we don't really know, but nevertheless, I think we've got a much better handle now on where FRBs are coming from, especially the non-repeating ones. Some of them actually play kind of hard to get. So one of the first ones that we did come across just after Christmas in 2019, when I looked at the optical sky maps for that patch of sky, I discovered that it was just in the glare of what is a star called Fomalhaut. Some of you may know this. It's only the 20th brightest star in the sky. And funnily enough, when you contact ESO and say, hey, we'd like to point one of your large telescopes at one of the brightest stars in the sky, is that okay? And they go, no, you are not going to do that because you will cause all kinds of mayhem. You'll not destroy, but you do long-term harm to our detectors. Fortunately, though, we were able to process a negotiation and came up with a way of covering over one half of the detector and putting the star behind that, and then try to look in the glare that was left over to see if we might be able to see a host galaxy. And in fact, after a lot of wizardry by Lachlan, we were able to pull out, yes, indeed, there is a galaxy there, and we were even able to measure the distance to it. So FRBs can run, but they can't hide. We will find them. Okay, now, before I tell you about what we can do, I need to step back a bit and make sure that everyone understands how we get to some of these results. So I want to tell you, for those of you who are not familiar with the concept of redshift, okay, so redshift, I'm sure many people are familiar with the Doppler effect. Okay, so if you're standing out on the street and you hear an ambulance coming towards you and the pitch of the siren seems to get higher and higher as it comes towards you, and then as it moves away, that pitch drops down. So the Doppler effect happens with light as well, but in space, you get the Doppler effect not just because of relative motion, but in particular, it's about the expansion of space between us and the source that emitted that light. So for instance, if we want to see, take a spectrum that is looking at the rainbow of colours from a particular galaxy, superimposed in that spectrum, we tend to see these bright emission lines from elements like hydrogen and oxygen from star formation regions within these galaxies. But as the galaxy is taken further and further away from us by the expansion of the universe, its light gets stretched out to longer and longer wavelengths. And the amount of that stretching, we call it redshift, and we give it the symbol Z, but it's the amount by which a wavelength is shifted away from its rest wavelength. And today we actually know of galaxies have had their redshifts measured even up to a redshift of 10 or beyond, thanks to the James Webb Space Telescope. But the only reason we can do that is because those lines have been moved so far out across the spectrum, out into the near-infrared part, so way beyond where our eyes or even our large optical telescopes can see. But that is exactly where JWST works best. So that's why JWST was built to do that, to look at the high redshift, and this particular high redshift means large distance, when back in time to when the universe was very young. But at the moment, we're just going to focus on redshifts out to about, let's say, 1 in terms of what we can do with FRBs. But eventually we hope to see them to even larger redshifts. All right, the next thing I need to tell you about is the so-called missing baryon problem. Okay. First of all, I need to tell you, when I was a student sitting in lecture theatres like this, studying astronomy, we were taught that the universe is made up of two things, so-called baryons, that is you, me, stuff that we can see, but actually about 80% of the universe back then was made up of what we call dark matter. So as the name implies, it's matter that we don't see, it doesn't emit radiation, but we can infer its presence and its amount by its gravitational influence on things like the rotation of galaxies or the dynamics of galaxy groups moving together, moving around each other. So we already knew that, bit of a mystery, and even today we still don't know exactly what dark matter is composed of, However, thanks to Brian Schmidt and his colleagues, who discovered through the accelerating expansion of the universe about 20 years ago that, in fact, dark matter isn't even the dominant component of our universe. Dark energy actually makes up 2/3 of that. Okay, and so dark matter, in fact, is barely a quarter of everything in the universe, and everything else, baryons as we call them, so again, the stuff that you and I are made of, stuff we can see, makes up barely 5% of everything in the universe. Sorry to disappoint you, that's all we are. What makes it even more frustrating, though, is that if we go out and try to count all that stuff, all the baryons, so add up all the mass from the light we can see coming from galaxies, stars and galaxies, gas and galaxies, dust, planets, people, horses, dogs, you name it, add that all up, and we don't even get to 5%. We get to about 2 to 3%. So where's the rest of these baryons, right? This is the so-called missing baryon problem. It's been around for a while. If you want, we know that baryons have to be there because that's what the Big Bang model that produces this that gives us prediction. Everything else seems to fit, except we only finding half of those baryons. So where are the rest of them? You would have to hide them somewhere. Well, all right. So one way you could hide them is if you could heat gas between galaxies, heat it up to say 1 million degrees. Space between galaxies is very, very empty, very thin, so you could spread the gas out. And if it was excited in some way, it might have been heated up in a galaxy and then expelled. But at temperatures of millions of degrees, the only way you could hope to see it is at X-ray wavelengths, okay? Because it's so hot, it can only be seen at X-ray wavelengths. Now we do have X-ray telescopes, they're on board satellites because they have to be above our atmosphere. And they're pretty good at picking out compact sources of X-ray radiation, such as disks of material spinning around black holes. However, they're not very good at seeing faint, diffuse X-ray emission, such as what the hot gas between galaxies might look like. So that is a way that you might be able to hide quite a significant amount of stuff in our universe, such that we would not be able to detect it with our current telescope systems. So this brings me to this plot, which was put together by our colleague Jean-Pierre Macquarie in 2020 and submitted to Nature, which is also the other most prestigious journal in science. And you don't get into Nature of Science unless you've got a pretty significant groundbreaking result. So what JP did is that he took the redshifts that we measured, that stretching of that light, effectively the distance to our first half dozen or so host galaxies, and he compared that against the amount of dispersion that we saw in the signal from each of the FRBs. And obviously, you know, as we'd kind of expected, the more distant the host galaxy, the more of that stretching of the light, but also the more of this ionized material that the burst must have passed through to get to us, and so you'd expect to see a higher dispersion, okay? And in fact, you can see this black line shows, yeah, it's kind of there, there's a bit of scatter, but it's not a bad sort of fit. However, this black line, that's not a fit to the data. That black line that you see, that is a prediction from the Big Bang model for why there should be 5% of the universe is made of baryons. And the fact that our data goes through that line so well indicates that we are seeing those missing baryons. They are there. They are the source of much of this added dispersion that would not be there if such diffuse material didn't exist between the galaxies. So, good news, the missing baryons have been found. You can relax. No problem here, nothing to see. I mean, look, we all kind of expected that, but this was the first direct detection of this material. There's no other way that we could have seen this without the existence of fast radio bursts. If we wanted to see this material, we would have dreamed up a phenomenon like fast radio bursts without knowing whether they actually happen. But they are out there in nature, and because we now know about them, we can begin to use them as probes of the universe. Sadly, just a few months after this result was published, JP passed away very young, a very sad loss to us. But in recognition of all the fantastic work that he had done, we always refer to this now as the Macquarie relation, whether Kraft and all the groups around the world trying to do this sort of work, we all call it the Macquarie relation because it was JP who really opened our eyes to the possibilities of things that we could do with fast radio bursts, such as finding the missing baryons. So from there, you might think, okay, well, we're getting out to redshifts about 0.5, 0.6. If we wanted to get to even higher redshift, surely all we need to do is to find fast radio bursts with even higher dispersion. So, for instance, you know, I would say roughly if you want to get to redshift of about 1, you probably need to find an FRB with a dispersion above 1,000, let's say. So it was quite exciting in 12th of September 2021 when we found our first burst with Kraft, which is at a DM dispersion above 1,000. This one about 1,200, so that was quite promising. So we sent the coordinates for this burst to the VLT, and they send us back these images at optical and infrared wavelengths, and there's nothing there, nothing that we can see. And that makes it kind of difficult. You can't really measure a redshift for a galaxy if you can't even see the galaxy. You don't even know. I mean, you might be lucky if it's just really, really faint. You might have strong emission lines, but it's just not the kind of study that we can easily say, oh, here's the most distant FRB now. Now, it might be the most distant FRB found to date, but until we get a confirming redshift, we don't really know. It could, however, also be the faintest FRB host galaxy ever found. That would be pretty exciting too. And so these were the conclusions that my student Lachlan came to when he published this result earlier this year. The jury is still out on this one. We're still trying to get more data. In fact, we put in a proposal to use the James Webb Space Telescope because we think this is really a fantastic way, probably the best way of ever being able to find the host for this thing. But we haven't yet found it, so more to come. Stay tuned. But on the 10th of June 2022, we found another burst which was even more distant, or at least we assume it is, because they have very high dispersion value. And this time, when we pointed the VLT out, it got the images back. Well, we went from having no host galaxy for the previous one to having, well, one, maybe two, possibly even three host galaxies. Which is which? It's kind of hard to tell at these distances just exactly whether it's one galaxy and maybe we're seeing multiple bright clumps of it, or, as we now believe, it's probably actually at least two galaxies coming together, interacting, and possibly even undergoing a merger, because this is the kind of thing that was happening in our early universe. So it's not unexpected that eventually we might find a fast radio burst in such a merging or interacting system. Well, first of all, we had to find out exactly how far away this thing is, and for that we used a spectrograph on the VLT. We put the slits to isolate just the regions we're interested in at a couple of positions, and then we sent the positions off to the VLT, and eventually they came back with this data. And although we have software that will analyse the data that's taken for us and process it and give us back a number, yeah, I'm kind of old school. I like to go and look at the data itself just to be sure that it really is what it's telling us. And so I was just scanning through some of the early results that came out, and I spotted these two blobs here, which I recognised straight away as coming from, most likely from oxygen, ionised oxygen, which normally in our local, in our own galaxy, would be at a wavelength around 3,700 angstroms, or 370 nanometers. But look down here on the scale, and we're way up at 7.5. We've almost doubled the wavelength. The expansion of the universe has shifted this thing out to a redshift of, well, in fact, it's just over 1. So, I mean, that's a nice milestone to reach. It's certainly the most distant FRB that we currently know of. And in fact, in our cosmological models, we can predict how old this burst is. And it turns out that this particular radio burst is almost 8 billion years old. I mean, our own sun is only 4.5 billion years old. This thing is more than half the age of the universe. It's travelled through space to get to us here today, and yet, until 5 years ago, we didn't have the technology to detect that type of burst. But thank goodness we did, because now we know FRBs are out there, and they've been happening for a long, long time. And if we can see them to this distance, we might hopefully be able to see them even further away. So this result was, again, pretty significant, the most distant one known. Now, these sorts of records don't last for very long, so we did submit it to the journal Science. It took us almost a year to get it through the refereeing and editing process. And thankfully, in that time, no one came out with a more distant localized burst, thank goodness. So we finally got it published in journal Science in October this year. And our wonderful colleagues here at Macquarie University put together a lovely media release to highlight the importance of this result. Not just that we had found the most distant thing, because records don't last, they're meant to be broken. But as I pointed out, the potential of such a high, more distant burst to help us, as we say, weigh the universe. So in other words, having just solved the missing baryon problem, we can use that finding to help us actually add up all the mass that really is out there and weigh the content of the universe. That's what we were getting at. And we were delighted a number of media outlets around the world jumped onto this and recognised it for the significance it had. Some other media outlets, though, somehow got, I don't know what media release they were looking at, but anyway, look, clickbait, call it what you will. There certainly was no mention of aliens in there, and I'm not saying it's aliens, but it could be aliens. But anyway, the fact is, these types of things do get noticed, and people are fascinated by them, as I hope you are as well. Since that paper came out, we did manage to get some observing time on the Hubble Space Telescope to go and take a closer look at this thing than we can possibly hope to get even with the best ground-based telescopes. And it turns out that there's probably not 3 galaxies or 2 or 3, there might even be as many as 7 all galaxies as part of the system. Again, not unusual, because we know that galaxies underwent an assembly process. They had a very violent past. And so again, the fact that this burst occurred in one of these objects that does seem to be having some kind of interaction. There's evidence for a bit of a stream of maybe stars or gas between them. And this type of activity, when galaxies collide, does certainly promote more star formation, elevating the numbers of supernovae and increasing the odds that you're going to produce a magnetar, which might still be the source for these FRBs. So that's pretty cool. What else can we do with fast radio bursts? Well, some of you may be aware that there's a bit of a crisis in cosmology. I mean, there's always a crisis in these things, but one of them is the so-called Hubble constant, which the name implies it's a relationship between how fast galaxies move, appear to be moving away from us, and their actual distances. And in recent years, we're getting increasingly precise values for the Hubble constant by looking at these type 1a supernovae that Brian Schmidt and his colleagues have studied, while other people have been looking at the results from the Big Bang, in particular looking at what we call the cosmic microwave background, which is the last remnant of the Big Bang. And the two of those can be used to deduce what the Hubble constant is. And they don't agree, which is a concern to some. Maybe the result will, they'll figure it out one method or the other. Perhaps they're not measuring exactly the same thing. But the fact that we have fast radio bursts, although any one fast radio burst, the Macquarie relation doesn't allow us to work out exactly how far away any particular burst is, because you could see there's a bit of scatter there. But if we do this for hundreds or even thousands of FRBs, the average value will give us a pretty good idea of what the Hubble constant is. And maybe it'll match one or the other, or maybe somewhere in between. We'll just wait and see. But at least it will be an independent measure. Other people would want to keep building on the Macquarie relation, go to even higher redshift and see how the fraction of these so-called baryons that reside between galaxies, how that might change as we go back to a time when the universe was much younger. There's suggestions that maybe photons, which of course carry light and radiation and therefore move at the speed of light, but they might actually, if a photon had a mass, even just a tiny amount, that would make a big difference to all kinds of fundamental physics. And one of the ways we might be able to constrain that mass is through studies of fast radio bursts. Other people are more interested in not so much where these bursts come from. They're actually very interested in the shapes of the pulses itself. I haven't got time today to go into that, but when we study those pulses at very high time resolution, so we're talking millionths of a second, they turn out to have all kinds of interesting structure in them that can tell us a lot about not just how the burst was generated, but potentially the material surrounding it, and possibly even the effect of gravitational lensing, which will be really exciting as well. Other people are interested in the other properties of the burst, such as that we can measure its polarization, and that can be used to help tell us about magnetic field strengths between us and the burst origin. If we have found enough of these at even higher redshifts than 1, let's say between at least 3 and perhaps out to 10, we can tell us about how the stars and galaxies came to heat up the universe, the so-called reionization. FRBs are a great way to do that if we can find them at high redshifts. And there's even the possibility to probe what are called the halos. Sometimes a burst will come on its way here, will pass not just through this hot gas, but it might happen to intercept not just a galaxy, but even the halos of galaxies, which are much more extended regions. And we can use these probes, a bit like doing a MRI machine, making a three-dimensional scan. We can do tomography, as we'll call it, three-dimensional studies of the structure of space, which is really exciting. But the thing about any one of these techniques, to do it properly, we're going to need not just a couple of dozen, we're going to need hundreds to thousands of localized fast radio bursts with their positions and distances to the host galaxies known. So the race is on, and we don't have this field all to ourselves anymore. Others have realized, well, hey, where they go, we need to go as well, but they don't have ASCAP. What they do have, though, so remember I told you about CHIME, that fantastic skateboard bowl, half-pipe arrangement? Well, CHIME itself is not great for localizing fast radio bursts, but they're deploying what they call outriggers, which are small subsections of these types of half-pipes, and they're located hundreds to thousands of kilometres away from CHIME across the North American continent. And they can use a technique called very long baseline interferometry, just kind of like the ASCAP, but blown up to much larger dimension. And with that, they'll be able to localize fast radio bursts to thousandths or millionths of an arc second. So crazy amounts of precision. And so that's just starting to get underway now. In South Africa, the precursor telescope to SKA is called Meerkat. It consists of 66 dishes like this. And although each of them doesn't have the same field of view that an ASCAP dish does, they have great sensitivity. There's many more of them, and so they can see much deeper into space. And so they are now just beginning to localize the first fast radio burst to a comparable precision to what we can do. Our colleagues at Caltech, of course Caltech don't like to be second to anything, and so they've decided they have to own this field. And so they've started what they call the Deep Synoptic Array, beginning with just over 100 dishes, and eventually building up to 2,000 dishes. But these are not fancy dishes, these are basically souped up versions of satellite TV antennas, because that's kind of all you need. And if you get enough of them, spread them far enough apart, and eventually they reckon you'll be able to find dozens of FRBs per day, which is great, but how you follow all those up with other ground-based telescopes, that's another matter. But even so, there are definitely big things happening there. And there's also a project called BURST coming out of colleagues in Taiwan, and that's somewhat low-tech. They're using what you call dipole antennas. This is a pretty proven technology, just to raise them on the ground. But by deploying these sorts of arrays across Asia, they too hope to be able to start localizing fast radio bursts at significant rates. So it's fantastic, but we can't rest on our laurels. We need to keep going, and we need to show that ASCAP is still at the cutting edge. It very much is. So at the moment, as I say, we've been finding a new fast radio burst on average about once every 2 months. That's probably in some ways good, because that's, in terms of getting follow-up, that's about all we can handle. However, we are very close to commissioning what we're calling the Craft Coherent, or CRACO, upgrade. And with this, we will hope to be able to detect not one FRB every 2 months, but maybe one every couple of days, which would be pretty neat. However, to do that, we've had to increase the processing power of our of a system that listens into the ASCAP signals. And it's been explained to me that the difficulty of the problem, well, it's like trying to watch 1 million YouTube downloads simultaneously and learn stuff from it, all right? So technologically, it's very, very challenging, and that's why CSIRO and other organisations are really keen on this, because it's pushing the limits of what we can currently do with computing technology. And it has great, obviously, scientific impact, but who knows what other benefits will come when we push the limits of the technology that's available to us, not just through hardware, but also through some very clever software. And because of this upgrade, we've now been granted time at the European Southern Observatory with a very large telescope. We've been given what's called a large program, which, as name implies, is a large amount of time. It's actually almost 180 hours over 2 years, which is a pretty significant chunk of time for a small country like Australia, competing against all the other member states of ESO. But we've got that time allocated to enable us to do the galaxy follow-up on at least 50 of these new fast radio burst host galaxies. So that's really exciting. So we're definitely still in the game here. And indeed, one of the messages I hope you go away with tonight is not just about how cool FRBs are, but the importance of optical and radio telescopes working together. Okay, so at the moment we have access to the ASCAP facility and doing these wonderful surveys, and we can piggyback on that. Thanks to a strategic partnership that was signed and negotiated by Fred's department, in fact, the Department of Industry, Science and Resources back in 2017, Australia, unlike any other country in the world, was granted access to the VLT on the same basis as any ESO member state, but only for a 10-year period under the strategic partnership. So it's an indication of just how important ESO sees Australia. We weren't at a position back then to become a full member state, but we hope to in the near future. But just that access alone that we enjoy has enabled us to do this kind of science. But we're already approaching the limits, really, of what ASCAP and VLT together can do. If we want to stay at the forefront of this field in the next decade, we're going to need not just the full square kilometre array, which is due to come online around the end of this decade, but we're also going to need access to this thing. This is called the Extremely Large Telescope in ESO speak, because it's even bigger than the Very Large Telescope. And those of you who came to last year's Allison-Levick Lecture would have heard from the Director General of ESO, Professor Xavier Barcons, would have told you how exciting this thing. This telescope, this is just an Ars conception, but it's already half built. This dome structure is not fully enclosed, but it's all built. The metalwork has gone up. And the mirror segments, casting is underway. This thing is going to happen before the end of this decade. However, under our strategic partnership, we won't have access to that ELT. However, if we can become a full member state of ESO from around 2028, that means we'll be able to combine all the data, fantastic results coming out of SKA, and we'll be able to follow them up, looking for indications of the FRBs and the host galaxies using the Extremely Large Telescope. So think what the possibilities of that would be. So hopefully by now you've realised that FRBs, fast radio bursts, but I think they really should have been called fantastic radio beasts. They're a great Australian success story. Okay, don't forget, the very first one was found with the Parkes Murriyang telescope. The first non-repeating FRB that was localised was with ASCAP here in Australia. We invented this field. We still pretty much own it. We're not going to be alone in that position very long, but we are very much determined to remain at the forefront of that effort. So where can FRBs be found? Well, they're found in galaxies not that different from our own. And in fact, I mentioned earlier, so the reason why we think there are magnetars are probably underlie most FRBs is because back in 2020, a known magnetar in our own galaxy started to emit radio bursts, which are kind of like an FRB signal, but much, much, much weaker. Interestingly, though, around almost simultaneously with that, we had an X-ray satellite that started detecting pulses of X-ray emission. So that suggests that, in fact, maybe FRBs do put out emission at other wavelengths. It's just that they are, unlike this particular magnetar, they're so far away, our current facilities cannot detect those other wavelengths. Our collaboration, Craft, has found was currently the most distant FRB known. Probably won't be that way for long, but nevertheless, it's good to be in the leading position for some period of time. But even this burst is 8 billion years old. So this burst occurred when the universe was less than half its present age. Think about that. And yet this discovery would not have been possible without both ASCAP, which told us where to look, and the Very Large Telescope at ESO, which enabled us to see what sort of galaxies exist there, where within that galaxy the burst occurred, and how far away it was. And in fact, so that really shows that the field of FRBs is really ripe now for exploration in the next decade, together with the power of the Square Kilometre Array and hopefully access to ESO's extremely large telescope, should Australia become a full member of state of ESO, will really finally start to be able to use FRBs as tools to help unlock many of the most fascinating secrets of the universe. Thank you very much.
Fantastic, Stuart. Thank you very much for an absolutely comprehensive and very, very accessible account of the world of fast radio bursts. Fabulous
Fantastic
stuff.
radio beasts.
Or fantastic radio beasts, that's right. So we've got time for a few questions. What I don't think we've got is a microphone runner, so I might be running up and down the aisles here. If we've got any questions for Stuart, there is one at the back. It's a pity you had to be at the back, isn't it? Can you shout? I'll repeat it if you will.
My question is just how much brighter are these tiny short bursts than the sort of the background data that's there? I mean, as in, you've said you can see them and they come up as a signal, but are our radios detecting them? They're just very brief and they don't interfere.
No, as well. Right now, you'd need obviously some of the largest telescopes on the planet to detect bursts, especially the more distant ones. However, for instance, if there was a fast radio burst comparable in scale, so I talked about the magnetar event in our own Milky Way galaxy that went off, but that was thousands of times weaker than any of those. But if there's no reason to suggest our Milky Way is really that different, suppose that there was an FRB kind of like the one that went off at this Redshift 1 galaxy in our own Milky Way, everybody would know about it because your mobile phone would start ringing. That is how bright these things would be. So the fact that that hasn't happened, because we've only had mobile phones, smartphones for a roughly short amount of time. But yeah, in terms of the ability to see them at large distances, so the good thing about them is they have such a distinctive signal. Okay, there's very few phenomena that will produce that kind of dispersion sweep, as we call it. The bad news is that we don't know in advance what the dispersion value is likely to be from any given burst that we detect. And the only way we can find them is we have to continually, in real time, be looking for, testing for all possible ranges of dispersion and looking for something that kind of fits. So that's why, part of the reason these things were so hard, we didn't realize they existed. It was only the last 20 years we had the computing technology that enabled us to do that rapid searching across such a large range of possible dispersions to go, oh, okay, that thing was not just a burst, but it was a burst at this very high dispersion value. Obviously, sometimes the data we get, the signal to noise, as we call it, isn't as high as we would like, but that's part of the upgrade that we're doing to the ASCAP now, is about increasing the signal to noise, if you like, and therefore hopefully picking up many more bursts at lower signal strengths than we are currently able to detect.
Thanks, Stuart. I think the idea of all your mobile phones ringing is a great, it's telling you that...
Welcome to the biggest astronomical experiment in history, everybody.
That's right, yeah. Any more questions? Another question? I actually have... Oh, there is one. Sorry. I can probably hold the mic for you.
Until when can we expect the ELT to be finished? And if it's finished before 2027, can we expect the strategic partnership to be extended to allow the use of the ELT for Australia?
That's two very good questions, and I'd like to defer to my colleague Fred, who works in the department that is the signatory to the strategic partnership and will be the main group leading negotiations with ESO for full membership. I would say, however, we're in my other hat, working for Astronomy Australia Limited as a program manager there part-time when I'm not working for Macquarie University. It's one of our number one activities that our company is working on right in the past year and well into the next couple of years. We are working closely with our colleagues, including Fred, in the department to build a case for full membership of ESO. Part of the case is built on, look what we've achieved just in the first 5 years of the strategic partnership. Wow, we've got world-leading results in not just fast radio bursts, but in other areas as well. So we'd like to think that would be enough by itself. However, we have to build what's called a business case. We have to explain to our members of parliament in particular, and members of cabinet, why it is worth investing significant amounts of money to become a full member of ESO. And that's not just about the science we can do, that's clearly an important bit, but there's also about the return on investment. What can Australia expect by way of industry contracts, for instance? And here again, there's good news. Australia has already secured some pretty major funding from ESO to carry out instrumentation and software projects on behalf of ESO. So things are looking good in that regard, but we certainly have our challenges to get this build this case to government for funding. Obviously, the current financial environment probably doesn't lend itself to significant new investment. But as you said, we do have, we're more than halfway through the strategic partnership now, but we are working hard and thanks to Fred and the department, to put the best possible case to government as to why it's so important that Australia become a full member of ESO, in large part because it will give us that access to the extremely large telescope, which is due to come online and have first light in 2028, and certainly from what we heard last year from Javier, he is determined that his organisation will do everything it can to make sure that it is delivered and working on time and on budget, and we very much hope to be a part of that going forward. Fred, do you want to say any more about the...
No, you've answered the question perfectly. Just a couple of things. My role in that all is quite small. I'm the person who cheers all my grown-up colleagues on from the sidelines, one of whom is here tonight. The department, it's the astronomy branch of the Department of Industry, Science and Resources, which has carriage of this work, and they're working very hard on, just as Astronomy Australia Limited is with Stuart and his colleagues. So it's an ongoing process, and we are crossing our fingers. The one loose end in your question, I think, and it's a great question, the strategic partnership ends on the 31st of January 2027. First light on the ELT is not going to be before 2028. The mirror itself has 798 segments to be polished and assembled together, and it's a big job. But as Stuart said, it's already over halfway. I think there's another question down. There's a guy called David Merlin with his hand up there, but I might... Can I put David on first? Question from David Merlin.
Yes, and your second point down there where you say in galaxies not that different, FRBs exist. What would the effects be if there was an FRB close to our galaxy or in our galaxy or in the Magellanic Clouds, for instance, especially if it was in our arm, a particular arm of the Milky Way?
Yeah, that's a good question. Well, as I say, fortunately, I guess for us, is that unlike, say, gamma ray bursts, which share a lot of common, they're very close in being acronym, GRB versus FRB. Gamma ray bursts are also associated with the deaths of massive stars, and they put out enormous amounts of energy, particularly at gamma ray wavelengths. Now, gamma rays are not something you want to be exposed to for very long. They can be pretty lethal. And there's been several theories about what would happen if a gamma ray burst went off with our own galaxy. It wouldn't be good, certainly, for the Earth's atmosphere, because it could do a lot of long-term damage. However, gamma ray bursts, we believe, are a lot like pulsars, and that the radiation is very much beamed along certain axes. And so, although there are some stars within our Milky Way galaxy that could potentially become a gamma ray burst at some point, as far as we can tell, they don't appear to be aligned just right, such that the gamma rays would be pointed straight at us. Now, fast radio bursts, however, generally they might be safer in the sense that most of their radiation seems to come out at radio wavelengths. And so, apart from being able to microwave a lot of popcorn in a very short space of time, that's probably the limit. We just don't know. But I think there are more than enough things to worry about that are trying to kill us in the universe already, without adding FRBs to that hit list, shall we say.
If I can just add a comment to that, I don't know whether you saw in the scientific press recently, there was a report of a gamma ray burst, which indeed did alter the Earth's atmosphere, even though it was almost 2 billion light years away. So they are interesting beasts.
When you say altered, it made the ionosphere bounce around a bit.
That's right.
So it definitely made its presence felt, but thankfully not in any particularly devastating way. Yeah.
Right. We're here to cheer you up, folks. That's.
Thank you. I have two questions. The first one is, outside of magnetars, what are alternative theories for the generation of FRBs? And the second question is, have you looked at how you could use AI to assist in the processing of certainly the large data and the increase in data that you're going to need to deal with?
Sure, okay. Two very good questions. So the first one, what else could FRBs be? Well, for a long time, the running joke was that we actually had more theories about what FRBs might be than there were known FRBs. That was certainly the case up until about 2015. Nowadays, I'm pleased to say, thankfully, there are many more FRBs known, but the number of theories, we've been able to eliminate a few of them, such as they might come from supermassive black holes at the centres of galaxies. Well, I think you'll have seen from those images I showed you, doesn't appear to be the case. There's other theories that in some way involve cosmic strings, which are kind of neat because we really don't know much about cosmic strings, but that's also a bit of an escape clause. We believe it's most likely, most of them could be magnetars. Now, as I mentioned, we did find a repeating fast radio burst in a globular cluster which shouldn't have any magnetars. Or at least so I was taught. It turns out, and as my colleague also DeMarco, who's in the audience tonight, she and her colleagues have been, because of the interest in gravitational wave events, which you probably all heard about, merging neutrons, merging black holes, and sometimes merging neutron stars and things coming together, there's been a fantastic outpouring of interest in what happens when two objects merge together. Obviously, some of them can produce gravitational waves that we can now detect here on Earth. But it turns out some of the things that you might form if you take, let's say, two white dwarf stars, which are objects which are not quite massive enough to become a neutron star, but are still a very dense state of matter, but maybe two white dwarf objects, which can be the remnants of a star a bit like our sun that can live, and they can hang around for billions of years. But if two of them were to merge, you might just hit that mass threshold and generate a neutron star, which in fact could therefore be a magnetar and an FRB. And so, we may still come back to this magnetar theory anyway. It's just that we have to find new and interesting ways to create them in environments where we didn't think they ought to exist. To your second question about AI in detection, that's a great thing. At the moment, we're still taking somewhat, let's say, a brute force approach. As I mentioned, we have systems that, as I say, they search the incoming signals or candidates for being an FRB, and we do a lot of repetitive checking to see, does it match this amount of dispersion? No, there's still a bit of slope there. Okay, is it a bit more dispersion? No, and until we get to something that looks about right, and go, okay, well, it's probably this amount. Perhaps in the future, now that we're finding more and more of these and we begin to understand more about their characteristic properties, it will become possible, and I know some of our colleagues overseas have started this process with their FRB detectors, is applying machine learning to improving our ability to not just find FRBs quickly, but indeed we may still be able to go back and look at older data that's still available in archives somewhere and search through those in a way that wasn't possible before, and maybe pull out signals from FRBs that happened many, many years ago. It's probably too late to do much with them now, but we might hopefully still be able to make better use of data that already exists and add to our ever-growing sample of FRBs that way. Yep.
Great questions. We might have time for one more. There's one at the front here.
From the radio burst, can we, at the moment, estimate the total amount of energy emitted by such an event?
Yeah, that's a very good question. We can estimate it, but the problem comes down to, since we don't really know exactly what causes a fast radio burst, some of the theories that we have, especially if they involve magnetars, will say that when the pulse is emitted, it will be emitted in all directions at the same time. And so for us to detect such a pulse at a long distance, it would have to be extremely energetic, so total luminosity would be enormous. However, if instead the phenomena emits radiation in a beamed manner, so kind of similar to these gamma ray bursts, or even kind of like those pulsar models, right, where the emission can really only find its way out along a very narrow cone. The good news there is that the total amount of energy involved is much less, and so they don't have to be as luminous for us to detect at large distances. But as a result, depending on what we assume about the cause of the burst, significantly affects the energy that's required to generate them. And so, for instance, we highlighted here, we found certainly the most distant fast radio burst that we know of. Now, people say, well, therefore, is it the most luminous one ever found? And we go, well, maybe, because it depends on what you assume about how much energy is being put out in all different directions or not. Not only that, but also, as I mentioned, the total amount of energy is confined to only a narrow region of the radio spectrum. Some of them, they definitely seem to have a cut-off at some high and low frequencies, but it's not the same for all bursts. And so unless you know exactly how much emission you got in total within the radio band, often your radio sensitivity cuts off, has to really cut off at some upper and lower bound. And yet we can see the emission clearly was going outside of that, and we don't know how much energy came out at other radio wavelengths. So it's a very fraught issue to deal with, how energetic was that particular burst, because there's so many assumptions built into it. But again, as we find more and more of these and we begin to get a better handle on what FRBs are, hopefully we can overcome those. I mean, to me, the amazing thing is all the uses we can put fast radio bursts to, and we don't know what causes them. It doesn't matter. They're just a tool. Everything's a hammer, right? So we go out there and we're going to use them, just as we still don't really know what causes type 1a supernovae, and yet they are the most precise distance indicators we know of in astronomy. So people use them to study dark energy. So we're not going to wait around for someone to solve the mystery of fast radio bursts. And there probably will be a Nobel Prize, whoever figures that out. But we're not going to wait for that. We are going to use them as tools because they are the coolest thing ever.
It's a whole new slant on science, really, isn't it? Not waiting for a Nobel Prize. I like that idea, Stuart. So, ladies and gentlemen, we've kind of reached the end of the evening. Events like this don't happen without a lot of help, and I'd like to thank colleagues at Macquarie University who have put in a lot of work to make this happen, notably Keller Sharpless, and thank you to Sam Muller for your introduction. I'd like to thank some colleagues from the Department of Industry, Science and Resources who handle the finances of the Allison-Levick Lecture, notably Lachlan McGee and also Rachel Horwood, who's here tonight. But most especially, I would like to give all our thanks to the 2023 Allison-Levick Lecturer, Dr. Stuart Ryder, for a fantastic presentation. And thanks to you all, too, for turning up, because without you, it would be pretty depressing up here. Thank you again. Safe journey home, and come again next year. Thank you.
Good night. Yeah, like I didn't even get onto the properties of the test. So. Good evening. What have I done? No, I just wanted to see if people were actually paying attention.
I was waiting to read what's going to happen. Like, is it going to be not?
Yeah, that's right. And you said not.
And you read it with not.
It's very hard. It's really hard to read.
Yeah, it is. You should never proofread range. I could blame ChatGPT.
You could. Good.
I didn't. No, I swear, none of this was written by ChatGPT. Thank you for pointing that out. I shall. The person responsible should take it.
Thank you very much.
You're welcome. Thanks for coming to the trial.
You say hello? Right. Are you going to go forward? And you French voice. So yeah.
No, it's just like... I went to Alpha Essays by 2002.
Yeah,
This I've been working.
they, thank God.
It's just amazing, beautiful.
I really
Yeah, I'm
enjoyed
sure
it.
you'll enjoy it. And hopefully, you might get to enjoy it.
So I paused to
That's very
decide whether or not I want
She's just
Okay. See you soon.
hello.
Thank you. It was wonderful.
Everyone, this is Matt, she said.
I oversee. I have actually
No, I got something to say. Thank you.
Yeah, no worries.
After physics and mathematics, obviously. Chemistry, thank you. I enjoyed the test almost.
Okay, good. Good. Yeah, exactly. Exactly. And no, it's all right.
What are the plans? You who are leading in space engineering in Australia, right? Do you have any plan to raise funds compared to other countries like USA? I mean, is there any technology you are planning to send to Moon? Since
Well, Australia is going to send a rover to the Moon within the next couple of years, 3 years. In fact, they've just come up with a name for it. They had a competition, the space agency had a competition, and they chose Rover.
since space capturing planet is very important.
Yeah.
Since Australia is a big country, but still housing is a problem. So
We have a number of challenges.
go to the moon and just capture.
Focus on the things we can.
Particularly, I know the North Pole. Everyone is trying South Pole. But North Pole.
Congratulations on what you've done.
All right, well, we'll hopefully that will do it. Yeah, so that's a separate, it's on the same site as astronomy. It's developed and built by a consortium at Curtin University, Perth. And as you said, the antennas just sort of very unusual, just the spiders on the ground. But it's fantastically powerful at lower radio frequencies. In particular, things like trying to measure that cosmic micro background. That's one of the things that we're actually thought to cosmic micro background. But we're trying to look for the very first signs of neutral hyperbolas. When the universe cooled, the Big Bang happened, the universe cooled down, and then heated up again. And we're trying to find that sweet middle in the middle where the universe is just pure hydrogen. Surprisingly, for something so virtually primitive, that's actually on the cusp of being able to form. They share some infrastructure. That's about it. ASCAP is a fully CSIRO funded and operated facility for all of the Australian astronomers and international. The MWA is operated by Curtin University, but has an Australian and international partners. But it tends to be a little bit more, a niche in terms of the science that it does best are not necessarily finding fast radio bursts. Although we've tried, for strange reasons, we're actually seeing fast radio bursts with MWA. Although similar arrays overseas that work at comparable frequencies, they have detected some, so hope to be able to overcome that shortly. But the SKA, the spec on array design for Australia is actually much more on that MWA model. So you've seen these Christmas trees, they look like Christmas trees, metal Christmas trees. Well, ASCAP, yeah, was an idea of what the square kilometre array might have become, but for various reasons it was decided to stick